So yeah, thank you for having me again. Now 3 years in a row becomes a habit. Yeah, so 10 years ago or so, I really liked to play around with a software called context-free, and it did, and it's still running, so you can still download it and run it, and it allows you to do nice, interesting, generative art, and the thing behind it is oh, I'm getting distracted actually. But yeah, welcome to the talk talking about my generation. And can we hear Mary? Will we heard her already? She's like luckily awake.
Yes, here I am.
Yeah, so after 10 years, I finally grasped ELF systems, and that's why I'm here, and I want to talk about it and describe it to you. And while I was very, happy to be accepted here, I saw Mary, whose work I'm following for many years already, that she did something with ELF systems as well, and in IXML, that she will present later. So that's why talking about my generation became talking about our generations. Let's first, because whenever I'm talking to other developers, they all say, yeah, ELF systems, I heard about them. But what are they actually? So Aristide Lindenmayer did in 1968 come up with a very simple way of describing the growth of algae and other like cellular cells and other things, and he came up with a rule set that we start with a symbol A, and for each iteration we will replace an A with an A and a B, and replace a B with an A. And let's have a look how that looks like. So we'll start with an A and replace it with A and B, and replace the first A with A and B again in the now third iteration, no, second, and the B with an A. And this is the fourth, and this is the fifth iteration of it. So there will be a tree of symbols is generated out of this. And if we're a nice, interesting side effect is that if you only count the A's in each iteration, you'll maybe notice a pattern emerging. So in the first iteration, it's 1, and then 1 again, then 2, then 3, and then 5. Does anybody? Exactly. I was sure somebody would know that. So yeah, Fibonacci numbers are in there. So the creation of Lindenmayer was then formalized into what we now know as ELF systems. And they consist of an alphabet. In our first example, it was A and B, just A and B and nothing else. And then an axiom, that's the point where we start, that was A. And then production rules, or rules, that an A is replaced by A and B by A. I need to speed up a little. Please give me some indication that I'm too fast, but I really want to save some time to show you something later. So yeah, I came up with an XML representation for such a system that you can see here. It has a root element system and an axiom. I combined then the rules and the alphabet into one element called grammar, where there's variables which have replacements and they match. Well, actually, match is no longer the case. It's symbol now, but yeah, this is how it's represented in Lindsay. Let's have a look at another system, the binary tree. If you look at the Wikipedia and everywhere else, the binary tree is everywhere. So this one starts with 0 and has more a larger alphabet. It has 0, 1, and 2 square brackets, opening and closing. And the rules are a little more complicated because the 0 will be replaced by a bunch of things that I'm just highlighting here so that you can follow. The 1 will be doubled each iteration. So any 1 that will be in there will infinitely grow or exponentially grow. well, two things are missing here, the square brackets. This is because those are terminals or constants, also called. And yeah, let's have a look how it looks when we go through the iterations. The first one is a 0, obviously. Next one is this weird little thing that we see there. And then it starts to grow in the second iteration already. I'm now jumping ahead to the 5th one, I think. This is this one here. I highlighted all the occurrences of the replacement of 0 here so that you can see, okay, now it's everywhere and hard to follow. There's a lot of 1s at the beginning and a lot of square brackets. That doesn't look not very much tree-like, right? So how do we get? So here's just an XML representation of the same thing in Lindsay again, which you don't have to memorize at all. But it doesn't look really tree-like. So how do we get to something that resembles a tree? The answer is we need production rules again, but this time we're gonna, yeah, draw lines. And there's one very old kind of drawing stuff in the internet, and that is, or in computer graphics, and is turtle graphics, where you have where you control a little turtle that you can say, yeah, go forward, turn, and then you can say, put your tail down or up, so that you'll either draw a line or just move, right? And so a lot of visualizations of health systems are using turtle graphics. So for our binary tree, we have the 1 that will be draw line forward. 0 is also draw line forward, but square brackets is the interesting one. It will push a state, so it will remember the position where the turtle is at the moment, and then turn right. So we branch at this point. And the closing square bracket will return the turtle to the last remembered position, and then turn left. So let's have a look. This is a 0, just a line. And then here is the first branch. So yeah, the green line is the first one to be drawn. Then the turtle will return to the end of the black line, and then we'll draw the purple line. And here is this next iteration where I only highlighted which of the branches is drawn first. And yeah, this is this weird thing that or this gibberish that we saw before, that's now something tree-like, right? Also, yeah, I haven't said that it's fractal, but I think Mary will cover that. Yeah, so in order for our system to be drawn as an SVG, you need to add a render element inside of the system in Lindsay, right? So if you don't put it in there, you'll only see the symbols that are generated by the replacements. And so you have the option to select which position you want to, or which box you want to show. And this is just piped directly into SVG view box. A thing that I really like. So a lot of people who know better than me already figured out what to do. So I just use that. And I don't have to document it also. So, and then I give it a starting state. So I say turtle, I place that turtle somewhere. And I will also give it some more information with it. I will say the orientation. So in starting from 0 would be pointing exactly rightwards. I think from your side, yeah. And then it goes counterclockwise as anything in mathematics do. Yeah, so that, well, actually, yeah. Orientation 90° would be upwards. And we also define an angle by which we turn. And that's 45 degrees by default for the binary tree in all examples that you find. And also a velocity, so how long will a line be when it's drawn? Then I found that, or Mary actually told me or showed me that Inkscape has a plugin that or also draws L systems, or is able to visualize them, but they only have support a standard set of elements or symbols. So we have A to F that will be draw a line forward. G to L will just move forward, so the tail is up and no line will be drawn. And plus, minus, and pipe will do the turning. And square brackets is just push state, and closing square bracket is just pop state. So you'll notice that we won't be able to draw our binary tree with that set of symbols. And sad, right? But we want to draw that. So we need to first translate it. I used these standard sets of Inkscape in my drawing function. So it already knows of those, how to do that. So if we now translate our L system into using those standard symbols, then we can visualize it. So here it is. It now starts with a B instead of a 0. And we have an A that is replaced by 2 A's. That is our 1. And the opening square bracket is followed by a plus because we need to turn also, not just push the state. And the same thing is when we pop the state, we also need to add a minus so that we turn right, left, right. I can't remember. Now we have here a set of terminals as before. These stay the same, but we had to add plus and minus. Still no image. Bear with me. Next one will be an image, I promise. We also have, I can also control the number of iterations this L system will go through, or that will be done in the topmost part. And here I'm just giving you again the entire, complete set of elements that you have to define so that you get an image. Here's your image. This is the binary tree, but it has only an angle of 0 and not 45. So this looks weird. And now I'm gradually, I'm already over my limit. I'm gradually modifying or increasing the angle, and our tree will unfold and become very untree-like, and then in the end fold in itself. But down here you see that it will the symbols stay the same all the time, so it doesn't change at all. And you can therefore, even with deterministic L systems, the ones that I currently showed you, already play around a lot and have wildly different results. Here's a lot of more interesting symbols that we found in our research, that some of them I have adopted, and some of them I plan to adopt. Some of them I already had, but so the multiply line lengths and divide line lengths, they were really interesting. And you can then, with those pointy brackets, you can have even more interesting results where you can then not only control the line length or increase or decrease the line length, but also have an option to have a thicker branch. Okay. Here's another one. This is how it looks like in Lindsay then. We have, because I'm using XML, I had to the pointy brackets I had to replace by LT and GT. Okay, the acceleration that I highlight here is the interesting part. Modifying this acceleration part, this also like you can get a lot of different results just by modifying this one value, and angle as well, as I already showed. Okay, let's not go into that. That's just how it looks in my function. At the end, it's just one switch. And yeah, let's get more interesting because stochastic, let's add a little randomness to it by stochastic L systems. Here you can see already the result of one. And yeah, if you look at the slides later, then you can also play around with it. This is how it looks in Lindsay. There's grammar type stochastic is the only interesting bit. And then also that we now have one variable with several options. And each of those options will be exactly 1/3 of probability of 1/3 to get selected. So I have one random number, and then I have 1/3 for each. And but it's much easier and efficient to summarize, to sum all the probabilities before selecting. This is what I've done here. There's, yeah, more to it. But I have to, but wait, what if one of those options should be more selected more often, right? So here I have added a weight attribute so that you can, yeah, with a probability of 10, it will be the first option and the next one as well. And option that it doesn't grow at all, the leaf, is very unlikely to happen, but it might happen. So if you just leave out the weight attribute, then it will be just 1, right? I really love seeded random number generators and trick people to implement them, several actually. Yeah, if you now set a seed, then you will always get the same. You will know which yeah, what the outcome will be. Okay. During my testing, I then found that my code was terribly slow, and even for stochastic systems, I even get stack overflows, which is nasty, and I haven't found the reason yet, I have to admit. So after 10 iterations or so, you get into problematic pieces. I then, for deterministic ones, you won't ever get a stack overflow, but it might take minutes to generate. So I came up with, yeah, ways to minimize the amount of symbols that are being replaced by just having a 1 being replaced by 2 and a 3 and a 4, so that when I so that all the ones that you first saw below the tree in the soil will become just 1 element, and therefore be also just 1 element in the resulting SVG, and that speeds up things. So you get 1 or 2 iterations out of it if you use that. So this is what it would look like. Yeah. Now here you see, I think this is really hard to see, but there's 6s, 4s, and 3s and 2s below the tree instead of 1s and 0s. Just here is what it looks like in my custom drawing functions, which you can always provide if you want to do some weird stuff that I haven't thought about. Then you can do that here. And this is also, when you look at it, you see that I'm now calling the same function with different parameters. And this is where I also want to hand over to Mary, because this is what she already managed to do and I haven't yet, and that is parametric stochastic systems. Mary, take, I don't know, hello? Okay.
Yeah, I'm trying to share my screen. Hold on.
I will switch the slides. Is that okay for you? I don't know if you can.
Oh, okay, sure.
Can you?
I'm okay. I'm sharing my screen, but
it doesn't show anything at the moment.
It's taking its time. I think my internet connection is not good. I'll just have you do it. Yeah, I'll just have you do it. Okay.
Yeah, but
okay.
I need to share
so
still. Sorry, Mary, because we can't. We don't see.
Are you showing? Just show your slides.
No, it does not show.
Yeah, just show the slides. I'll tell you when to move.
Yeah, but then we can't hear you, Mary.
You're on Zoom, so if your screen gets
I'm talking. Can you not hear me?
We can, but we can't see the slides at the moment. So if you all open the slides in your browser window now. Okay, cool. Okay.
And you can think of these as being functions with no parameters. And what parametric systems do is give you functions that do have parameters. Hello. Sorry, I'm looking at the wrong screen. Okay. And so, whoops, Jesus. It's too early in the morning. So here's a evaluation. Here's a rewrite rule for the symbol A, but the symbol has parameters. So it has this sort of little functional form with this $n as the parameter. And then the rewrite rule is going to have little expressions in it involving this parameter. And in the case of this one, a couple of global ones like $A. And then what's going to happen is during the generation, those expressions are getting evaluated and put into the string. So I'm using Saxon XQuery function to do this. So I'm using XQuery syntax for my little expressions, as you see. And then there's sort of a pseudo evaluation that happens in interpretation where we're parsing out these little functional forms and then figuring out what function to call and passing in those numerical values. And then if you put it all together, so in my implementation, I use maps as my representation for the systems. So here's the rewrite rule we saw before for that symbol A and the axiom. Here's the binding of the parameters. This is going to be passed into the XQuery function along with the specific parameters of the symbol to do the evaluation. And then I have a map of bindings for the arity to distinguish. And I have a few built-in ones as well. And then you run this for, in this case, a few hundred times, you get this nice little spirally design. Peeking ahead, sorry. Okay. Now I want to talk about using invisible XML and some experiments I've done. This isn't my main implementation, this is experimental. And in the first instance for parsing the output. So when you're interpreting the string, you go symbol by symbol and do what it says, draw a line or turn. But that's not actually what is going on. What's actually going on is I'm calculating all the puts. And when I get to something that breaks the path, I put them all together and emit to pre-parse out the path structure. And so this is a little invisible XML grammar to sort of give you the sense of how that would go. A path is a series of these moves plus maybe some control variables that are just used for generation we're going to ignore. So we use the minus on those. And then a branch is a set of nested paths and branches. Problem, this is an ambiguous grammar. If you think about a path like f plus f, it could be a path, it could be 3 paths, it could be 2 paths. And it's actually hard to write an unambiguous grammar that doesn't forbid paths you want to allow. But I'm using CoffeeSax here, and CoffeeSax provides this choose alternative option that lets you specify a function to use to resolve the ambiguity. And the function I use is what I call the greedy function. It looks at the available options and picks the one that has the longest leading match. And this is super intuitive. It's like how a lot of regular expression matchers work. It's really easy to write a grammar that does what you want with this. So I suggest to IXML implementers and standardizers out there, it would be swell if this were available as some kind of standard option. And so now with that in hand, I can parse a string like this and get the path structure. So the leading path, the intermediate path inside the branch, and the trailing path, just as I want. And now I can process this maybe a little more directly. As I said, experimental. I haven't actually done that yet. Let's think about it for generation. So this is called a tur-dragon. There's its rewrite rule. And to turn this into an L system, first of all, the root just matches all of the symbols. But any symbol that has a rewrite becomes a non-terminal in the grammar. And I'm going to ignore it because I don't really care about XML structure. And so here's the rewrite. We match F, we chuck it out with minus, and we insert what the rewrite said we should insert. And we run this for a few generations, and we take the string values because we don't care about XML structure here. And it works great. Performance is not as good as a more direct implementation, but it's a pretty direct. You can write code fairly easily just to translate it to an IXML grammar. So that's pretty cool. Let's push the envelope just a bit. Stochastic tur dragging here, where 80% of the time it bends one way and 20% of the time it bends the other. We're going to follow the same process. We got two alternative rewrites. We have two alternative branches here, and there they are. Couple of problems. First, this is wildly ambiguous, and we've also lost the distribution, the random distribution between these. And I'm going to abuse copy-stack's choose alternative here to do both. Here, I look up the context symbol, determine what random distribution I should use for it, and choose based on that distribution. And this also works great. Also, performance not as good as a more direct implementation. I want to switch gears a little bit now and talk about, we've talked about what L systems are. We've talked about how they work, some alternative implementations. I want to talk about what they're for, particularly in the context of visual arts. And this may seem weird. We've seen plenty of visualizations. But I want to step back and instead ask the question, well, what is it about them that makes them interesting? What do they give us? And the first thing they give us is recursive self-similarity. We take a line and we bend it. And then the next generation, we bend those bends, and then we bend those bends. And we do this for a few generations, and we get this beautiful fractal structure. This is Sierpinski's arrow. And it's no accident, because what L systems give us is a terse declarative representation of rules of self-similarity that is at the core of fractal behavior. The other way to look at recursive self-similarity is, as we've seen, organic growth. No accident here. This is what Lindenmayer was trying to model in the first place. And you think about how a plant grows. It grows for a little bit, and then it turns at a particular angle. It grows for a particular bit, and it turns at an angle. So this is a lovely example. This is a Barnsley tree. And, if we wanted to make it sort of more organic, there's a lot we could do. We've seen already, we could change the interpretation. We could use stochastic systems. We could use parametric systems. And there's a lot there that we could apply. The other thing that L systems give us is structured rule-based pattern generation. For this example, I'm using a random axiom. We'll see why in a sec. And there are the rules. They're very simple. 0 goes to 0, 1, 1 goes to 1, 0. And when we run this for a few generations, we get a long binary string, which I am now going to interpret as an integer sequence. And there's lots of fun things you can do artistically with integer sequences. Follow me on Mastodon if you want to see more. But I like this one because it shows the structure. You have one sequence controlling the horizontal. And that's going to tell you how to flip bits as you go column by column in the first row. And the other one controls the vertical. And that's going to tell you how to flip bits as you go row by row in each column. And you end up with this pattern. And if I use a random binary string, this would be a mess. But it's not, because there's structure to the string, which comes from the structure of the rules. And rule-based pattern generation applies in a lot of other domains. You can generate music, not just the visualization of it here, but actual musical tones. You can generate linguistic information. Here's a little stochastic system to generate random sentences. You can generate architectural. Here is a hotel in Mumbai with L system generated columns. And we've really barely scratched the surface here. There are context-dependent systems. There are bidirectional systems. There's all kinds of other interpretations you might apply. So go have fun, go experiment. It is a little addictive, but here's some resources to get you started. And that is the end.
Thank you very much. Can you hear me already?
Yeah. Thank you both. So anyone has any questions for Juri or Mary?
Do we have time for questions?
Let's do a quick round of questions.
I will stick around, and I think Mary will be maybe in the chat, definitely. Or
Sid,
Mary, can we hear you?
Sid.
Yes,
you have
yes,
a
I'm
question.
here.
We can't hear Sid.
No, that was just an applause.
Nico, we can't hear Sid.
That was just applause. It wasn't actually a raised hand.
Ah, anybody with a raised hand? No? Yes, we'll move on to the next presentation. Thank you once more.